Hey guys, what's up? Today we are going to be looking at how to visualize audio. So all you're going to be needing for this project is, of course, an audio file. For example, right here I've got a song from Position Music, which is a library I can use on YouTube. Okay, so as soon as you got your song, it can be some voiceover, really anything. Once you've got that, I am going to go ahead and just start creating a new script. And this is a script that's going to be taking care of pretty much everything, so I'll call it Sound Visual. So for that sound visual script, we're going to need a few things in here. The first thing we'll need is an audio source that's going to be playing our song file. The second thing we'll need is a float array called samples, and another float array called spectrum. Of course, you can name them anything you want really, but we'll just stick to those names. And finally, a float called sample rate. Okay, so now we've got all of these fields. Let's go ahead and initialize them in a private void start. The first thing we'll need is actually get our audio source. Now, assuming our audio source is going to be on top of our object, I am simply going to say get component. And then let's initialize our sample to a new float array, and then we're going to be defining how big is going to be our sample. I recommend using 1024 here. Same thing for the spectrum, so spectrum is equal to a new float array, and then let's use 1024. Okay, and then finally the sample rate. Sample rate is something we're going to be reading from the file itself, so we're going to say audio setting output sample rate. Alright, so now this is all the setup we need to actually read some values out of the audio file. But what kind of values do we want to read actually? There is three that we could read. I'm actually going to make them public so we can have a look at them in the inspector. The first one is going to be the RMS value. So RMS is the average power output of the sound. And then the second one we'll be using is the one you'll pretty much use at a lot of places, is the dB value, so like the sound value during that exact frame. And finally the pitch value. Okay, so those are the three actual values we're going to be calculating every single frame. Now, since we're talking about every single frame, we are going to need an update. So let's do private void update right here. In that update, I'll actually branch out to another function that we'll call analyze sound. And this is taken from a thread I seen on Stack Overflow. Some guy actually made some good research on that. I will link to it in the description below. It might actually help you understand the whole sound reading aspect. But if you just want to skip that and get the formula, just tag along. We are going to be writing it right now actually. So every single update frame, we want to analyze the sound. Now, when we analyze the sound, first we need to get the actual output data of that current frame. So we'll do source get output data, and then it takes in a float array samples, so that's our sample, and then it takes in a channel. We're listening on the channel 0. Now what's happening here is that sample is actually being passed as a reference because it is an array. So the values inside of sample are going to be modified, and we'll get the result back inside of sample. So we don't have to say anything. We don't have to say sample is equal to this. It's going to be modified while it's ran in the function. Okay, so now what we're going to do at this point is get the RMS value. So let's get the RMS value, and this one is actually done by getting a sum of all the squared sample. Just bear with me, we're going to be writing it down super fast. Int I is equal to 0, float sum is also equal to 0, and then we're going to be calculating it inside of a for loop. So for, we already have our int I right here, so I'm going to remove it. Leave the semicolon right here. So as long as I is smaller than 1024, that's our sample size. In fact, what we could do is actually put it up here as well. So let's do private const int sample size, and since this is a const, I'll just put it in all caps. And we can actually modify this float array, this one too, and this number as well. Now let's actually add it to the sum. So sum is equal to, and we said we wanted to have the square value, so sample at the index I times sample at the index I, which is going to give you the square value. And then afterward, once we've got that, we can actually do the square and get the RMS value. So RMS value is going to equal matf dot square root, and we're looking at sum divided by sample size. And this is going to return you the RMS value. Now, once we have that RMS value, we can actually start calculating the dB value, and it is fairly simple to do from there. So we'll get the dB value. All we're going to say is dB value is equal to 20 times matf log 10 using the RMS value, and you could divide it by some kind of reference value. So I'll be using 0.1 in here, and that's a formula I've got from the post I was talking about, and there's more description in there if you want to actually learn how this is done and why this is done actually. Now moving on to the fun part, this is where we actually get to visualize our data. So we get the sound spectrum, and to do so, let's do source get spectrum data. Same thing as before, we send in our array, and then the channel is going to be 0, and then the window is going to be FFT window, and we're going to be using Blackman Harris in here. Alright, so we've got the RMS value, we've got dB value, we also got the spectrum and the sample array. The last thing we would want to do here, if we would just follow the thread, is we'd find the pitch value. And I've also included it up here, but I'm not going to be using the pitch in my example right here. In this video, we're not going to be using the pitch at all actually. So what I've did is I've just copied over what's on the thread. So if you want to actually get the pitch value, you can do that. Copy this formula over, but I'm not going to be using it. So if you guys want to, just pause the video, copy this over, and we're going to be moving on to the next step, which is to actually visualize that audio. So if we just take a step back right here, just make sure we collapse our function. We have our start. In our start, we assign these things. In our update, we analyze the sound every single frame. That is, of course, assuming a sound is playing. So if we just jump back in the engine really quickly and we have a look at our game, let's go on the main camera. Why not? Let's drop the sound visual on here, and we are going to be using an audio source as well. So I'll just type in audio source, and we'll add a audio clip to it. The audio clip is going to be the one we've imported, and we're just going to start playing this. Alright, so I don't know if you guys can hear me well, but we have the sound playing in the background, and if we have a look at the main camera, as you can tell, our values, they keep changing every single frame. We have the RMS value that changes, we have the dB value that goes up and down, and we also have the pitch value. So all of these values just keep jumping up and down, and that's what we're going to be using to visualize our audio. Now, of course, this is only working when I'm playing the game, and our audio is actually running in the background. Alright, so what we're going to do right now is we're going to take this a step further. We're actually going to start spawning a line of stuff, a line of actual like primitives, and then we're going to be moving them around. So I'm going to go just beneath the start and start laying down a new function that I'll call spawn line. And this is only for spawning a line of visual that's going to be moving with the beat. For this to work, I'll be using two new arrays, so let's go ahead and declare those at the very top. First one's going to be a public transform array, and it's going to be our list of visuals, so visual list, and it's going to contain every single object that is actually moving, and we need the actual transform to modify the scale. And then afterward, we're going to be using a private float visual scale to know exactly, say we're on object number 4, then what is the scale of object number 4. And finally, we're going to be using one more number that we'll call amount of visual. So private int amount of visual, and this is going to be used so we know how many of those primitives we want to span. So if we're spawning cubes, then we're going to be spawning 10 cubes one next to each other to actually move with the beat. So back to our spawnLine function, we are going to declare our two array. Visual scale is going to equal to a new float array of size amount of visual, and finally the visual list is going to equal to a new transform array in this case. Visual list new transform array that has the amount of visual in it as well. Now let's actually iterate through that. So for int I is equal to 0, as long as I is smaller than the amount of visual, we are going to go ahead and just start spawning objects. So the first one is going to be, well, all of them are going to be game object geo, and we are going to do game object dot create primitive, and let's actually create primitive of type cubes. We're going to be creating it as a game object because we're returning the value. And then afterward, we can go ahead and just say Visualise at index I is equal to geo.transform. And then we can also move it, so Visualise at index I is equal, or actually Visualise at index I dot transform is equal to a vector3.right times I. So that's going to span them 1 meter, that position, that's going to span them 1 meter apart. So this is our spanline function. Let's make sure we actually call it inside of the start. So I'm going to go at the end of the start and just span the line. Now if we head back in our game for a second, and I'm going to mute the audio for now so you guys don't hear it, we are going to hit play, and as you can tell, we span 10 different cubes, one next to each other. So here they are. Now those 10 different cubes are supposed to be moving with the beat, but right now they're really down. So what we're going to be doing is we are going to create a function that is actually being updated every frame. So below update right here, we are going to create another function called update visual. So update visual, and this is where we are actually going to this is where we're going to be modifying the scale. So let's start with 3 different int. The first int is going to be visual index is equal to 0. The second one is going to be spectrum index, also equal to 0. And finally, we're going to be also including a average size int, and this is going to be the sample size, so in that case 1024 divided by the amount of visual. So for every single cube we have, we are going to get a certain amount of the sample. So say if we had only 2 visual, then we'd have a 512 sample per cube. So we'll do while visual index is smaller than the amount of visual, so in that case that's 10 iteration, int j or g is equal to 0, and then we'll do a float sum is also equal to 0. From there we are going to do another while loop, so j is smaller than average size. In this case, let's just go back to say we have 2 visual. It's going to be a little bit easier to explain. So we run this while loop twice, and then while j is smaller than 512, because that's sample size divided by 2. So we're running this 512 amount of times, basically times 2, so we have the whole sample there. We're going to say sum is plus equal to the spectrum at that very index, so spectrum index. Then afterward, we're going to say spectrum index plus plus. We're also going to increment j. Okay, once we have this, we can actually start calculating the size. So float scale y is going to equal to the sum divided by average size times a multiplier that we want. So let's go ahead and just type in, we can be having a multiplier of 10. Of course, we'll make this public, so let's go to the very top here. And let's make this a public float visual modifier. Let's call it like that. And we can put some crazy value in here, like 50. Okay, let's go back and actually remove the 10. And let's place our visual modifier in here. So basically, we are going to be taking the whole sum, dividing it by the amount of the sample, and then multiplying it back to actually have something we can see. Else the number would be way too small. So while we're up here, I'm also going to create another field, a field called smooth speed. And this is going to be used to actually reduce the size of the actual visual over time. This way, like I said, we're not just snapping on to up and down values. We're just going to gradually just make them go a little bit smaller over time. So let's do smooth speed is equal to, say, 10 in that case. And we're going to be using it back in our update visual function. Once we've calculated our scale y, we're going to say visual scale at the visual index, that's our array, is minus equal to time the delta time. So that's for the previous value we had in the last frame, times smooth speed. Now let's just assume that that previous value we had is smaller, so visual scale at the index visual index. Let's assume that that value is smaller than scale y. Then what we want to do at this point is make sure we bump it back up to what it should be. So visual scale visual index is now equal to scale y. What this is going to do is that if your value is actually smaller on the next frame, we are not going to go straight down to that lower value. We're going to slowly go down with the scale of our object. However, if it shoots back to a very high pitch value, then we want to be snapping instantly up so we can give that burst effect. We can give that like that power effect when it goes up, but when it goes down, we gradually let it fade. And then let's go ahead and just modify the value of our object. So visual list, now we're actually affecting the actual transform. So visual list at visual index dot local scale is now going to equal to vector3 1 plus vector3 dot up times the visual scale at the index visual index. Okay, that might be a little bit complicated, and trust me, it's not that complicated, but it's not that easy to understand either. Hopefully you can understand with the actual example we're about to shoot. So we're going to say visual index plus plus afterwards, so on the next iteration we can actually affect the second object. Let's have a look in our game. Let's actually go back to the amount of visual really quickly and put that on, say, 64. So we're going to be creating 64 cubes. Okay, so I am on mute, I believe. You guys should not be able to hear the music in the background, but here are the 64 cubes. Now, of course, they're not moving because we're a bit stupid and we forgot to add it to our update. We have the update visual function. Let's go ahead and put it right inside of the update, just like this. And now let's go back, play this, and hopefully we can get some result. And as you can tell, we start getting some result. Something you're going to figure out quite fast though is that when you're sampling a song, you're only going to have a lot of activity in the first few cubes, but then at the end here, it's going to be kind of dead, and that's, to be honest, that's really boring to watch. It has a little bit of activity. If you look at the number up here, it moves, but it really doesn't move that much. So this is why first we added a visual modifier value. Of course, you can just bump it up. As you can tell, it's going to do a lot of changes to the thing, but again, this one dominates pretty much all the rest. Now you could actually enjoy this. I personally think it's a little bit bland. I think we could actually try to spread it a little bit more. So what we'll be doing is first we'll clamp that value because that value is way too high. It's going way too high for me. So I'm going to be putting a maximum on this one, and I'm also going to make sure I remove part of this. So say I want to get rid of that part. I want to get rid of 50% of that line. If we just put everything here on a single line, let's say we get rid of 50%, so we only have these guys moving here, the orange part moving. That could be something I would like. So what I'll do now is I'll head back into the actual code, and we are going to put a maximum value on this. So at the top here, I'll do a public float that I'll call max visual scale, and let's put that on a maximum of, say, 25. Now to implement this, it's going to be fairly simple. We are going to go right here in our code and say if that visual scale at the index visual index is bigger than max visual scale, then we're simply going to bump it back down. So visual scale at visual index is now equal to max visual scale, and this way we just clamp this upwards, so it can't actually go further than this. Now about only keeping 50% of the line we've had, what we're going to be doing is we're going to add a new value, another public float, I'll call keep percentage, and we're going to put that on, say, 0.5, so we get 50%. Now the only place where we need to modify our code for this to work is over here in the average size. Instead of saying sample size divided by the amount of visual, we are going to take that sample size, multiply it by our keep visual, and then make sure we cast this as an int. So we go like this, we cast this as an int. Actually cast the whole thing as a hint. And let's actually have a look, see if we see any difference. So let's say we only decide to keep the 10 first percent of that line. So we're gonna go up here and say 0.1. We only keep the 10 first percent. And as you can tell, the first line we've had a little bit earlier is now spread over quite a few cubes, as you can tell. So we could actually leave it like that if you wish. I'm gonna go with 50%, so 0.5, and we can also bump up the visual modifier to, say, 150. See if we can actually hit the cap as well. And do we hit the cap? We don't actually hit the cap because the cap is at 25. We could actually put that on, say, 10. So the max visual scale could be 10. We can bump this up again to, say, 175. Keep a little bit less, so maybe 0.25. Now I'm just playing with the value, of course. Try and make this look good. This is something I like a little bit more, and as you can tell, we do hit the cap here. And it's gonna work with what I want. Okay. So that's only a line though, that's a little bit boring. Well, I mean, that's an audio spectrum. We are going to push this a little bit further. Now, of course, if you like it that way and you just want to go with that, you do you, but we're going to push that a little bit further and actually create a circle. We could be creating a circle. So back in my code, I am going to go at the very top here in the start. I'm going to comment out the spawn line. We're not going to be using spawn anymore. We're going to be using spawn circle, which is a new function we are about to write. Now for spawn circle, the things are pretty much the same actually. So we're going to start by declaring our array, our visual scale array. We're going to say it's equal to a new float array that contains the amount of visual. If I can type, okay. Now afterward we're going to need a center. In that case I'll just be using the transform.position for the center. So wherever my object is, wherever my camera is going to be the center. Or actually that's not going to work. Let's actually put that on vector 3.0, so the middle of the universe for this case. Else it would just span around the camera and we would not be able to see it really. Let's also declare a radius. So what's the distance in between the center and then the actual radius of the cube? Let's go ahead and say 10 meters. And we can also, I forgot to declare, the visual list is equal to a new list of transform, not sorry, list, array is equal to a new transform array, and of course the amount of visual. Alright, and then all we need to do is run a for loop in which we spawn our cubes. So we're going to create a for loop and double tap on tab so we can actually see it. And what we're going to say in here is, as long as I is smaller than 0, as long as I is smaller than the amount of visual, I plus plus. Then we need to get a angle. We'll do float angle is equal to I times 1.0f, so we can actually have this as a float, divided by the amount of visual. Now with this we can get the actual angle using p. So angle is equal to angle times matf dot p times 2. And then we're going to be using two floats to float x. We're going to say float x is equal to the center dot x plus matf dot cos using the angle times the radius. Same thing for y, so y center dot y plus matf sin this time, angle and radius. Okay, with these information we can actually get the position of the thing. So let's do vector 3 position is equal to a new vector 3 in which we're going to say x, y, and 0. Let's also make sure we add the center to this. So center plus this new vector 3, and that's going to give us the position of the cube. Now let's go ahead and instantiate it. So GameObject.geo is equal to GameObject create primitive type cube. And we want to be, of course, creating this as a game object. Okay, so we've got our game object. Let's move it, and let's also make sure we rotate it in the right way. Since it's actually always scaling up on the y-axis, let's make sure the cube is rotated so we can actually have the spikes going in the right direction. So let's start with the position. Geo.transform.position is equal to pos. And then geo.transform.rotation is going to equal to quaternion. Look rotation, we're going to use the vector 3.forward as the first vector, and also for the forward, for the up, we're going to using the actual position you're at right now. Okay. Now once we're done with all of that, we span our cube in the right manner. Let's actually add them to the visual list. So visual list at the index I is equal to geo.transform. And just like this, we should now be able to spawn a circle. So back in our start, spawn circle. Let's go ahead and just try to run this now. And as you can tell, we get a fairly nice circle. And the things are still playing. Now obviously we can be changing it a little bit so it looks better. You could wait until the bass kicks in so they all start moving, or you could be saying we reduce the keep percentage to say we only keep 10%. We can also increment the amount of visual, so I haven't made this public, but we could also make this public. Or actually reduce it could even look better. So what if we actually reduce that by 2? We only run with 32 here. It looks something like that. It looks like this, it's kinda a little bit too much, but still, we're able to play with these values as much as we want. Now, that doesn't look really cool either. We need something else on top of that. Of course, if you want to keep this and go ahead and just make your game, you can do that, but I'd like to actually have something more in here. What I have in mind right here is to actually add some kind of background to this so we can actually use the dB value for something. So what I'll do is I'll just take my camera, just make sure I pull back to say until I can see everything, so say -22 is going to work in my case. Of course, I can just reduce the maximal visual scale as well. I can say that's 7.5, who knows, and we end up with something like this, right? I like to actually cover this whole area with a plane. So what I'll do is I create a new plane, make sure I rotate it in my direction. So let's rotate it this way, that's -9 degrees. Then we can go inside of the game view and actually position this, or actually scale this up properly. So let's go ahead and do 7.5 in X, and as far as Y goes, we're not modifying Y, we're modifying Z in this case. So maybe 3 in Z. This way, I actually get this kind of result. Now with the shadow, it almost looks cool, but let's actually modify the scale of the background as well using the actual sound decibel value. For this to work, we're going to be using some new fields, so let's just put them at the very top here. We're going to be using a float called background intensity right here. Also the material, so public material, background material, and 2 colors. Let's do public color, minimum color, and also public color, maximum color. Okay, with these 4 fields, we can actually calculate something quite simple using the dB value. So let's head down to our update function. We are going to say update background. Now obviously update background is a function we haven't made just yet, so let's just go down here and do private void update background, and let's start writing it down. Okay, so what we're going to need in here is fairly simple. We're going to start by reducing the intensity of the background. So background intensity is minus equal to time the delta time times the smoothing value. We can be putting the same exact smoothing value as the other one, so smooth speed, which was equal to 10 if I recall. Now what we'll do here is we'll say if the background intensity is smaller than the dB value this frame, then we're going to say background intensity is equal to that dB value. So again, we are going to scale up if we need to in a single frame, but if we have to scale down, we are going to slowly, gradually scale down. So we have that burst effect as well when we just go up, but we don't have it when we go down. Now once that's done, we're going to be using the background material. We're going to be changing its color for a color that we're going to lerp. So color.lerp in between the minimum color and the maximum color. We're going to say background intensity here. Now the way lerp works is it's going to be using a value in between 0 and 1. Now what I'm scared is that background intensity might actually go a lot beyond that value. Because dB value can go up to say 20, 30, can go up to some high values. So we're going to be putting a cap on this by dividing it by say 20. So that would be my cap, right? If it goes above 20, then we are at the maximum capacity of the actual color of the background. So we are at the brightest if it's on 20 or above that. And just like this, we should be able to have something that works. So let's go back here. Let's create a new background material. So create material. Let's call this background material, and we're going to drag and drop it on our plane. Now here is the plane, and we can just modify, see if it works. So as you can tell, this kind of works. We could also be putting a little light in the middle, why not? Since we are able to play with the shadow a bit, that could be something that looks good. Let's put that in the center. So 0, 0, 0. If we just move it a little bit towards here, bump the range to something quite big, so we'll say 50. And we just go from here. We have a few bugs, of course, because we haven't set our value, but that doesn't look too bad, right? Let's go on our main camera and actually set those values. They're looking for the background material, which we haven't drag and drop, so let's do that right now actually. Put it right here, and now we're looking for a minimum and a maximum color. So what color do you want your background to be when it's at the lowest sound it can be? We're gonna go with something blue-ish, maybe something like that, some really dark values, because really there's no sound playing at this time, so let's put it fairly dark. And then I'm gonna be copying this value over to my maximum color, but then I'll be cramping it up here in the blue, so almost super bright blue. If we play this now, we should actually have something that looks good. Okay, so obviously we have some problem here where the background doesn't actually jump to the right color, and that's because the background intensity is actually inverted here. So what we'll do is we'll head back to our code, and at the very end here where we do the update background, we're going to be swapping this around. So we're going to be using the negative value of background intensity. We're also going to be swapping minimum color for maximum color in this case. So let's just swap these two, and let's also increase the dB value to say 40, because I saw it was in between 10 to like 40, so we want to be making this a little bit higher. And this is the kind of result we get. Now, still a little bit too flashy, at least for me. I think this is gonna like give you some seizure. So we might want to be reducing the smooth speed, but only for, say, the background in the back. So right now, as you can tell, I reduced the smooth speed, and obviously it's not gonna work for the actual cubes, but for the background I think it looks just fine. So 0.5 seems to be working. What I'll do is I'll simply remove the value we have here, smooth speed, and I'll put 0.5 here instead, and we're gonna end up with a result that is a nice balance of the two. So if that doesn't look good enough, you can also swap back to the lines. In case you prefer the line, simply uncomment this line and comment the circle one, and then you can actually play the line. If we just put some music in here, you can actually listen to it, and it matches with the sound. Now, of course, you have a lot of settings to play with on the right hand side, and you just have to keep looking for what's going to be good for you. You can also be changing the color in between two awful colors if you want, like blue and red. But it's really up to you at this point, and I hope you're creative with this. I hope that you can use the spectrum to actually make something that looks cool, and who knows, you can even spark mechanic out of that. So if you were just if you just like try and put, say, a sphere here, let's add a rigid body to it, and I'm just messing around at this point. It's not something that I would usually do, but if I just take a sphere here, let's go ahead and just put a mass of 5, let's lock the position in Z, create a bunch of those. We just go like this. Oops, that's on the wrong axis, but we just have a look at this, and we could actually create some kind of little game out of that. Who knows, or just some kind of effect. So at this point, it's really up to you. Make something that looks cool, and I hope you guys enjoyed this tutorial. I hope you learned something, and if you did, please leave me a like on the video. Really appreciate that. Leave a comment as well. Just give me like feedback on what we could be doing next. And also check out the Facebook page, the Patreon page, and all those other kind of stuff. That keeps me going, guys. Thank you so much for watching, and I will see you in the next one.